What would happen if you ran Claude Fable 5, the most powerful and expensive AI model on the market, 24/7 to rewrite your entire product from Zig to Rust? The team behind the popular JavaScript runtime Bun actually did this. After an intense 11-day sprint, the team ended up with a staggering final compute bill of $165,000. In this video, I will go over exactly how they pulled this off using loop engineering, and the massive problems they inevitably face along the way. First, what is Bun? Simply put, Bun is a lightning-fast all-in-one toolkit and runtime for JavaScript and TypeScript applications. It's designed as a drop-in replacement for Node.js. Recently, the AI company Anthropic acquired the team behind Bun. The reason comes down to a dependency risk. Anthropic specifically relies on Bun because it packages Claude Code into a single cross-platform executable file. This provides lightning-fast cold starts and requires zero local dependencies for the user. By acquiring Bun, Anthropic eliminated their dependency risk and secured total control over the runtime powering their product. But they had a fundamental problem deep in the code. Bun was originally written in Zig. Zig uses manual memory management, while JavaScript relies on an automated garbage collector. Mixing the two caused constant memory leaks and hard crashes. Standard debugging tools couldn't solve the core architectural clash. This prompted the Bun's creator to initiate a total rewrite into Rust, a language renowned for its strict memory safety guarantees. Doing a manual rewrite would take a group of human engineers a full year and force a freeze on all new features, and that's just not an exaggeration. Just recently, language creator Richard Feldman published a breakdown of a manual rewrite for the Rock compiler. They did the exact opposite, moving 300,000 lines of code from Rust to Zig. Doing it completely manually by hand took them 487 days. Therefore, the team decided on an all-at-once strategy. Used Claude to translate 500,000 lines of custom code into one massive sprint. The AI-specific job was to rewrite the roughly 500,000 lines of custom Zig code that acted as a glue binding all these components together. Letting AI agents translate code file by file without a master plan would instantly lead to conflicting patterns and mismatched code. That's why they spent the first morning generating global blueprints. Specifically, they created two central documents, Porting and Lifetimes. Portings acted as the strict syntax and pattern rulebook for the translation, while Lifetimes explicitly mapped out how memory should be handled across different components. This gave the AI a strict unbending set of rules to follow. To execute this, they built a 4-step AI assembly line that ran continuously. The implementer tasked strictly with writing the code, 2 adversarial reviewers tasked strictly with auditing the code, and the fixer responsible for committing the accepted code. And finally, the automated compiler responsible for verifying the build. This setup was designed to defeat author bias. Usually with humans, the person reviewing the code is not the person who authored it. The person writing the code wants to merge, which biases their actions towards shipping before it's ready. Claude behaves the exact same way. The Claude instances that wrote the code naturally wants the code to get accepted. The Claude instance that reviews it wants to find issues. To maintain objectivity, they use split context windows, one implementer paired with 2 or more adversarial reviewers. The reviewer's only job is to find bugs and list reasons why the code does not work. The implementer does not review and the reviewer does not implement. Things broke almost immediately. Having 64 AI agents working simultaneously in the same folder was a disaster. They kept running global commands that wiped out each other's progress. In just 2 minutes, the agent completely corrupted the codebase. They had to halt the loop entirely. The solution they landed on was to ban the AI from running global commands and to split the project into 4 separate folders. This allowed the 64 agents to commit code simultaneously without locking up Git. When fixing compiler errors across a million lines of code, manually editing individual files simply does not scale. Because of this, the team instituted a strict rule. Focus on fixing the process that generates the code instead of hand-fixing the code itself. If something broke, the human engineers edited the global blueprints or the loop prompts. Those corrections were then automatically applied by the agents to every other file in the codebase. And of course, they ran across more problems. Because the AI was forced to pass Rust's incredibly strict compiler, specifically the borrow checker, it found a lazy loophole. Instead of actually fixing complex memory logic, the sub-agents started stubbing out the failing code. They would delete or bypass the logic entirely, leaving paragraph-long comments explaining why their workaround was fine. The team had to harden the adversarial reviewers with an absolute override rule. If a piece of code requires a massive comment to justify why it is written that way, reject it immediately and force a real programmatic fix. If they tried to compile 500,000 lines of Rust as a single package, the compiler would be too slow, completely bottlenecking the AI's feedback loop. Jared, Bun's creator, decided to shatter the architecture into roughly 100 separate crates, so the Rust code would compile faster than the 64 AI agents could work in parallel. But splitting the code triggered a nightmare of cyclical dependencies, where crate A needed crate B, but crate B needed crate A. When they finally fixed the architecture and ran the compiler, the newly separated crates threw a terrifying wall of 16,000 compiler errors all at once. Code generation had to be paused. They ran a targeted workflow to mathematically untangle the dependency paths, and then distributed those 16,000 errors across 64 agent grid to clear the entire backlog simultaneously. Running 64 agents in continuous error clearing loops requires reading the global blueprints and massive code files millions of times. This burned through 70 billion tokens. Without intervention, this would have generated an estimated $1.6 million compute bill. To avoid this, they utilized prompt caching. You might think caching just 2 reference files wouldn't move the needle against 500,000 lines of code, but the AI doesn't read the whole codebase at once. It processes tiny files one by one. To get just one of these files to successfully compile, the agent might run 20 iterations, rereading the exact same 50,000 token rulebook on every single try. That repetition meant the master rules actually accounted for over 92% of the total data processed over 11 days. By freezing the porting and lifetime rules at the very top of the AI's memory, the system read the rules at a 90% discount. This single optimization kept the final build to a still massive but manageable $165,000.
I am never going to financially recover from this.
Once the code finally compiled into a single Rust binary, they had to verify that it actually behaved exactly like the old Zig version. If Bun's testing relied on traditional unit tests, which validates individual functions and modules internally, this 11-day sprint would have been dead on arrival. Unit tests are strictly bound to the specific language implementation. Changing the codebase from Zig to Rust would have forced the team to manually rewrite hundreds of thousands of lines of internal test code alongside the application. Instead, they relied entirely on behavioral-based integration tests because Bun's massive test suite was written completely from outside in TypeScript. It treated the runtime as a literal black box. The tests didn't care about the internal implementation, they only verified how the final compiled binary behaved. This decoupled the architecture meant the AI could completely hollow out the inner Zig engine and swap it for Rust. And as long as the final binary still handled JavaScript the exact same way, the tests passed perfectly. The new Rust binary had to run flawlessly across Windows, Mac, and Linux hardware without skipping a single step. They moved the final battleground to Cloud CI pipelines. Over days 8 through 11, the AI iterated through 135 full test builds, constantly failing, adjusting, and retesting. Finally, on day 11 at 6:23 a.m., build 54,202 passed for all systems. Because this was a strict 1-to-1 mechanical translation, about 4% of the codebase still relies on unsafe Rust. As the team moves forward, they will systematically refactor those unsafe blocks into safe idiomatic Rust. However, the Bun team's victory is already live. The Rust rewrite is currently in production, powering Prisma's Compute Public Beta and Claude Code itself. It delivers a 20% smaller binary and stopped the endless memory leaks they were tracking. Of course, because they're owned by Anthropic now, they'll do anything to show that their overlord's AI system worked. But I personally think that this is a monumental achievement, considering a year ago, large language models could not produce a single file that worked out of the box. Marketing stunt or not, when an 11-day loop prompt replaces a 500-day manual rewrite, the baseline for what software engineering looks like has officially changed.